biggest, most stubborn problems in theoretical physics.
Oh, yeah. We're talking about trying to bring together general relativity and quantum mechanics.
Yeah.
The heavyweights.
Exactly. Two incredibly successful theories, right? General relativity gives us this beautiful picture of gravity on the grand scale, planets, stars, galaxies. It's all about the geometry of space-time.
Smooth, deterministic, yeah. But then you flip to the micro world, and quantum mechanics rules. It's amazing at describing particles, forces, but it's all probabilities, discrete packets of energy happening in this sort of fixed, flat background.
And they just don't mesh. Fundamentally incompatible principles, really.
That's the crux of it. GR needs space-time to be dynamic, curved by matter. Standard quantum mechanics, it assumes space-time is just a static stage.
And attempts to, force them together, quantize gravity like the other forces.
Well, that's where things get messy. Mathematically, it tends to lead to, well, infinities. Nonsense answers, basically. It tells us we're missing something fundamental.
Okay, so into this difficult spot comes a really interesting idea, quite intuitive actually, the vibrational ripple hypothesis.
The core idea is, well, you know how quantum particles have this wave-like nature?
Sure, wave-particle duality.
Right. So this hypothesis says, what if that wave isn't just like a mathematical description of probabilities? What if it's a real physical thing, a ripple in something?
A physical ripple. Okay.
And then here's the leap. What if that ripple is the distortion in space-time, the thing we experience as gravity?
Whoa, so the gravity from, say, the Earth
would just be the combined effect, this sort of cumulative hum of all the individual ripples from every single particle making up the Earth.
Okay, let's unpack that. That's a pretty profound claim about reality, isn't it?
It absolutely is.
And straight away, it seems like it bumps up against the usual way we think about quantum mechanics, the Copenhagen interpretation.
Exactly. Because in the standard view, that wave function is just potential information. It describes possibilities. You measure it, poof, it collapses into one reality.
It's not a continuously existing thing.
Right. And you can't have something that pops in and out of existence be the constant source of gravity, can you? So this ripple idea, it needs the wave function to be physically real.
Yeah.
All the time.
Which points towards
what?
A different interpretation.
It strongly suggests something like a realist interpretation, where the wave function isn't just about what we know, but about what is.
Okay. So our mission today is to dig into this. How does this ripple idea try to bridge that gap between the quantum world and curved spacetime? How does it, connect to Einstein's equations? And what are the huge hurdles it faces? Because it sounds like there must be some big ones.
Oh, definitely. But let's start with that quantum wave itself. The Schrödinger equation tells us how it behaves, right? The psi function. But yeah, the big question always was, what is psi physically?
So if the ripple idea says it's physical, what does that really mean for things like wave-particle duality, how we interpret quantum mechanics?
Well, like we said, the standard Copenhagen view treats psi as epistemological. It's about our knowledge. Superposition before measurement, collapse upon measurement. A kind of potentiality cloud.
And that ephemeral cloud just can't be a steady source of gravity.
Precisely. It lacks the necessary persistence, the physical reality.
So if not Copenhagen, what does work? Is there interpretation where the wave function is more solid, more real?
Yeah, this is where you really need to look at something like the Broglie-Bohm theory, pilot wave theory.
Ah, okay. That's the one with hidden variables, right? Deterministic.
Exactly. In that picture, the particle always has a real definite position. Always. And it's guided, literally steered, by a real physical wave, the pilot wave. This wave follows the Schrödinger equation, too.
So the wave function isn't just probabilities, it's a physical field, an ontological thing.
That's the idea. It's a physically existing field guiding the particle. And that gives the vibrational ripple hypothesis its anchor. The ripple is essentially this Bohmian pilot wave, seen as physically real.
Huh. So if this turned out to be right, it wouldn't just use de Broglie-Bohm, it would kind of prove it by giving that pilot wave a huge physical job, creating gravity.
It would be a massive validation, yes.
Yeah.
It connects the interpretation directly to a physical phenomenon, which is pretty neat.
Okay, so if the ripple is gravity, it has to connect to Einstein's picture, general relativity.
Absolutely. You go from special relativity space-time as one fabric to GR, where gravity is the curvature of that fabric. Wheeler's famous line, right? Space-time tells matter how to move. Matter tells space-time how to curve.
And the how is spelled out in the Einstein field equations. Geometry on one side.
and the stress-energy tensor, T, on the other side. That tensor basically tells space-time, here's where the energy is, here's the momentum, the pressure, all the stuff that causes gravity.
So for the ripple hypothesis to work, that particle's ripple has to be its contribution to 2.
Essentially, yes. The ripple itself, its properties, most directly translate into the stress-energy tensor for that particle. The ripple is the source term in Einstein's equations.
But hang on, this sounds a bit like semi-classical gravity, doesn't it? Treating the source, the ripple, quantumly, but keeping spacetime itself classical, described by GR.
That's a very good point. And doing that leads you straight into a notoriously difficult problem, the back reaction problem.
Or the loop. Spacetime curvature affects how the quantum ripple evolves.
The ripple is what's creating the curvature in the first place.
It's a feedback loop from hell, basically. Chicken and egg.
Exactly. The geometry depends on the field. The field depends on the geometry. You need a self-consistent solution. So the ripple hypothesis, while intuitive, inherits this massive, unsolved conceptual problem.
Okay, so let's maybe break down the ripple idea into its core claims. First, the wave part of a particle is a real physical field, the ripple always there with the particle. And we've seen that leans heavily on de Broglie-Bohm.
Right. And it's interesting, this idea of a physical wave isn't totally out of left field in speculative physics. People have explored ideas where maybe mass itself comes from some kind of space-time vibration.
So there's a conceptual resonance there, even if the details differ. Like maybe the ripple is a standing wave or something to do with virtual gravitons.
Potentially. It connects to a lot of deep questions about the nature of particles in spacetime. The second claim is that this ripple isn't just causing curvature, it is the local curvature. It's the physical form of the particle's stress energy.
That's where the math would need to get really specific, right? Building T from the wave function.
Precisely. You're not just putting a quantum field on curved spacetime, like in QFT in curved spacetime. You're saying the field generates the curvature. And yeah, that brings back the back reaction problem with a vengeance. You'd need to solve coupled, highly nonlinear equations.
And people have actually tried to model this kind of self-interaction directly, haven't they, with the Schrödinger-Newton equation?
Yes, exactly. That equation basically adds a gravitational self-potential to the standard Schrödinger equation, derived from the particle's own wave function. It's a direct stab at modeling this gravitational feedback.
And it leads to some weird predictions.
Fascinating ones. It predicts that if an object is massive enough, its own gravity could sort of force its wave function to collapse, to choose a state.
Like gravity itself is causing decoherence.
Yeah, gravitational decoherence. Roger Penrose is a big proponent of this idea that gravity is fundamentally linked to quantum state reduction. So the ripple hypothesis, simple as it sounds, connects directly to these really advanced, cutting-edge research areas.
Wow. Okay, and the third claim. The gravity we actually feel from big objects like planets is just the sum total, the collective effect of all those individual particle ripples.
Right. All 10 to the power of 50-something particles in the Earth, each contributing its tiny ripple.
But summing them up can't be simple, can it? Because gravity affects gravity. Einstein's equations are nonlinear.
Exactly right. It's not just a simple addition. The ripple from one particle would affect the spacetime that its neighbor's ripple exists in, and vice versa. It's an incredibly complex interacting system.
So you have this huge challenge. How does this frothy, rippling quantum spacetime at the smallest scales average out to look like the smooth, predictable spacetime of general relativity that we see?
That's the emergence problem, and it's a beast. How does classical reality emerge from this quantum substrate? If the universe is fundamentally this sea of ripples, our smooth, everyday world is, in a sense, a large-scale illusion.
And this isn't a unique problem just for the ripple idea, is it?
No, not at all. It's actually very similar to a core challenge faced by loop quantum gravity. LQG pictures spacetime as being built from discrete quantum loops, atoms of space.
Okay.
And a huge hurdle for LQG is showing how arranging enough of these discrete quantums perhaps somehow gives rise to the smooth, continuous spacetime of Einstein's theory at large scales. The ripple hypothesis essentially faces the same kind of emergence problem, just framed differently.
So thinking about the bigger picture, where does this ripple hypothesis fit? Is it more like string theory or loop quantum gravity?
That's a good question for context. String theory usually starts with a fixed background spacetime, and strings vibrate within it. It's background dependent.
Right.
Loop quantum gravity tries to be background independent. It doesn't assume space-time. It tries to build it from quantum principles. The ripple hypothesis feels philosophically closer to LQG in that sense. It's suggesting spacetime emerges from the collective behavior of these matter ripples.
So it doesn't presuppose the stage, it tries to generate the stage from the actors.
Something like that, yeah. It makes its fundamental approach quite different from typical string theory.
So we could classify it as a kind of emergent gravity theory.
Definitely. It proposes gravity isn't fundamental, but emerges from something deeper. But its specific mechanism emerging from the physical reality of the pilot wave makes it pretty unique among emergent gravity ideas, which might invoke thermodynamics or entanglement instead.
Okay, so let's try to wrap this up. We've taken this deep dive into the vibrational ripple hypothesis. It's conceptually, well, quite appealing, isn't it? An intuitive picture for gravity's origin, trying to mend that GRQM split.
It is appealing. And we found its internal logic really hinges on adopting a realist view of quantum mechanics, specifically something like de Broglie-Bohm. The standard Copenhagen view just doesn't give the wave function the kind of continuous physical presence it needs.
But, and this is the big but, when you try to make it concrete, it doesn't magically solve quantum gravity. It sort of repackages the problem.
Yeah, it inherits some of the deepest challenges. That back reaction problem, the self-consistency loop, is front and center. How does the ripple shape space-time while space-time shapes the ripple?
And then there's that massive emergence problem. How do countless interacting ripples smooth out into classical space-time? It's the same kind of tough question loop quantum gravity faces. We also touched on the Schrödinger-Newton equation, trying to model that self-interaction, even predicting gravitational decoherence.
Right, which is fascinating in itself.
So, final verdict on the vibrational ripple hypothesis. Where does it stand?
Well, I'd say it's a really compelling conceptual model, a philosophical picture almost. It offers this nice story connecting the quantum and the cosmic. It fits nicely with background-independent ideas like LQG, and it's a unique take on emergent gravity.
Yeah.
But it's not really a scientific theory yet, not in the full sense. The main issue is the lack of a specific predictive mathematical framework.
It needs its equations.
Exactly, without a rigorous mathematical structure that can, 1, reproduce general relativity where we know GR works, and 2, crucially, make new, testable predictions that differ from current theories. It remains a really interesting physical idea searching for its mathematical form.
So, if someone wanted to push this forward, turn it into a testable theory, what would they need to do? What's the research program?
Well, first, you'd need that formal math. Explicitly define a stress-energy tensor using the de Broglie-Bohm pilot wave, perhaps.
Then tackle the equations.
Yes, solve those coupled Einstein and Schrödinger or Schrödinger-Newton equations. Find self-consistent solutions, which is incredibly hard given the nonlinearity.
And show it works for big stuff.
Demonstrate the classical limit, yes. Show how all those interacting ripples average out correctly to give us the smooth space-time and gravity of planets and stars.
And the clincher. A unique prediction, something we could actually go out and test.
That's the gold standard. Maybe a tiny deviation from GR near a black hole, or in the very early universe, something falsifiable that only this theory predicts.
Okay. So a lot of work needed, but let's end with this thought. Just imagine for a second, if this or something like it was right. What if gravity isn't fundamental? What if it really is just an emergent phenomenon, this continuous symphony rising from the universe's tiniest vibrations? What would that imply about reality, about space-time itself?
It would be a revolution in understanding, wouldn't it? Opens up completely new ways to think about the fabric of existence. Definitely something to chew on.